recording. All right, so I'll spend as much time as you guys want on the three exercises that you did in your last exam. And we can play around with these numbers. I'm going to do a file save as so I don't write over this. Okay, so 6.1 was a drawdown, fairly classic drawdown behavior for radial flow. We're plotting pseudo-pressure versus the log of time in hours. And this graph pretty much tells it all. We haven't done our type curve yet to make sure that we have the right data. But annotated on this is the straight line that we're going to use to calculate the perm. So it pretty much indicates which data point should be used for linear regression. The red dot at the very end indicates that we're still in radial flow. In other words, we always use our last time point in our radius of investigation equation, assuming that the last data point is still on infinite acting flow. If it curves away from that, we would use the point at which time we're curving away from that, because that's when we are assuming we're seeing a boundary. And then the yellow triangle, red and yellow triangle on the left of the graph is the pseudo-pressure of 1 hour. And it looks like it's the y-intercept, and that's only because our time scale starts with 1 hour. If we would have had some data before 1 hour and we were plotting it so that we had a scale, a y-axis over here of 0.1 on a log scale, we would have had a different y-intercept, but we still have that value for the pseudo-pressure of 1 hour. And so most of the results are listed there. I calculated a perm from that data of 0.124 and a skin of 1.47. Now, for some reason, some of you did not use pseudo-time, which would have been a function of pressure and time. And since it's a drawdown, no superposition was required. And we calculate a pseudo-pressure prime. And in this case, since we calculated perm, your multiplier for both your P sub D and your T sub and your P prime, although I've got them as functions, but it would have been a function of the perm of 0.124. So that's your level setter there for, that's what I multiplied all my pressure derivative points by, my delta pseudopressure and my delta pseudopressure. In this problem we had some H2S, some of you didn't catch that. And our skin was a slight positive value of 1.24. With me it's like there's a near zero skin. It doesn't make too much difference if it's a 0.5 to a minus 0.5. And then in that 1 to 2 to 3 range, those are fairly normal positive, negative skins. And a positive skin of 10 is horrible. A negative skin or 6 or 7 is about maximum. You can't get very large negative skins. And then again, annotated on my semi-log plot that I got 616 feet for my radius of investigation. And I used a previous template that assumed that I could calculate an early time slope. Remember, that'd be just pressure versus time Cartesian for wellbore storage. So then with that, I would, if you were able to calculate, somewhere I use that, I probably use it in a function. A lot of times, instead of writing the equations like I do in class, I'll just use a function. Oh, I'm sorry, I'm on the wrong point though. My T sub D match would have been a function of C sub D. And I would have used that early time slope to calculate my T sub D over C sub D coefficient. Early time unit slope for wellbore storage is required for a C sub D calculation. So I guessed it. I trialed and errored C sub D. I'll try to get this type curve and that slope. I can't get both of the same. I'm going to zoom in just a little bit. So I was looking for the students to get close to a good type curve match. Your level setter was calculatable. Knowing perm, you should have been able to put the altitude of your red data, your derivative data, which looks like it's mustard yellow or something like that, on the graph. So there's only one variable that I really didn't know because I don't have any data on my wellbore storage dominated region, unit slope line. Without any data there, I can't make a unit slope. Now, you could have just guessed T sub D over C sub D arbitrarily, or the way I did it, I really only had one unknown, and so I guessed that arbitrarily. And I'm going to zoom in on my type curve just a little bit now. So I consider this a fairly good fit. You can't really get this exact, but if you look at my red data points, they follow, except for my very first one, are all on a line. If I change that, there's only one curve that I can really get that data to fit to. The pressure derivative data actually does a fairly good job also. It's all following one line. Really, all the data points are on one line. So my T sub D multiplier, and a lot of times you had the reverse of that. So 6.39, or if you had 0.15, I notice a lot of people use that. My T sub D is a multiplier, but somebody uses it as a divider. And we can look at other people's multipliers or dividers and see how much difference that makes if you want to. If you want to shout out one you looked at and kind of discuss the case why that wouldn't be as good, we can. But I was looking for a fairly tight range. On this problem in particular, I can get within about 10% of my multiplier and get a pretty good match on that. I'm not really solving for too much here in addition to what I've already solved for on my semi-log plot. My semi-log plot gives me perm and skim.
I'm curious, did you just kind of look at our summary answers and grade based on those, or did you look at our fits?
Yeah, on the portion of the answer sheet, oops, got too much information there for the students to show there. I actually did this on this problem. The most variety of answers were in that T sub D multiplier, right?
Okay.
So I would cross plot. I went through once and kind of graded all the papers. And then I cross plotted how many points. Let's say I gave you maybe 5, 4, 3 points. And then I calculated a percent error. And I went through this on all the problems. And then if the error was very small, you would get a 5. And so I went back after I graded everything, and sometimes I found some points that were out of, I looked at it, that's a 3, I looked at it, that's a 2, but then I went back and made sure that I had a monotonic fit of how I scored everybody. So somebody that had a closer number to my number should have got a higher score
Okay.
than somebody that didn't. I spent a lot of time trying to make sure this graph was consistent. That's why when we flashed over to that other page for my scoring, I put in your numbers. I copy paste your numbers next to mine, values, and then I calculate a percent error. Yes.
What actually you consider for giving the marks? You were exactly looking for the exact answers, or you also grade for the concepts or the procedure? The procedure is right. Like in my case, I just only forgot to convert the days into hours in the 6.3. So my whole analysis was here and there. What my procedure was wrong was
The Halliburton cement engineer made a miscalculation on the Macondo well. Probably not as big as a factor of 24. And now, some $180 billion later and 11 deaths because of a miscalculation. Okay? Now, I have two kinds of tests in here, right? When I have a short answer test, you're able to put down the concepts and the knowledge that you have. But when you make a calculation, I expect you to be able to get it. Especially like in this chapter. We worked the examples. You had access to these exercises. You could have worked the exercises. You could have asked questions about the exercises. I expect you to be spot on. Getting the concepts, we're done with that. We ran through the concepts in the class. So, disappointingly to you, I'm looking for the number. I'm looking for the right answer. And I'm looking, and then I downgrade relative to the percent error. Now, that percent error had to be tighter. In other words, the standard deviation around what people gave me from permeability is real small. The standard deviation for what they gave me for the T sub D multiplier was pretty wide range. But I modified, in other words, I gave some marks even though the T sub D multiplier was a larger percent error. But I expected a fairly tight range for permeability. Okay.
My only concern is that, like, because I don't know how my own was graded, like I have no idea how many points I got for K or skin or whatever, that I don't know what the...
Oh, yeah.
You see what I'm saying?
Yeah, I have that information.
Okay.
I have a 2G grid with everybody's name and everybody's points.
Yeah.
And now, how to disseminate that information? I could have put it in D2L, but then it would have been pretty time consuming. But I actually have that information.
Okay.
So that's a good point.
My point being that I have an extremely good curve fit, but like my skin is off from yours by like, I don't know, 50+%.
Yeah.
But I don't know if that's worth a 5 or if that's worth a 1. I don't know.
Yeah. I'm with you. I don't have, a lot of times when you turn in papers, I turn it back and write the marks on them. I do have that information. I can't just pull it up because it have all the other students' names on it.
Yeah.
But what I can do, I'm thinking of what I can do. I mean, I can, I can, strip out everybody's marks per, I'll get it to you.
Could you said you did this cross plot thing here?
Yeah.
Could you post that without the identifiers?
The fastest way for me to get it done is I use one cross plot and kept changing the inputs, so the cross plot for each previous one is not saved.
Oh, okay.
Let me finish this one thought, because I got to write it down. I think everybody's interested in individual marks per line item, and that may require that I just strip out from the Excel spreadsheet and email it to you. I think I can do that, considering the small size of the class, in short order. I'll get that done.
Okay.
Okay, question back here.
I realized the variability on the scheme was close to mine, 0.12 then. But the spreadsheet I sent to you, you must have seen a spreadsheet that the old type curves are the same, and that was exercise 6.2.
I haven't heard anything you've said so far.
I'm saying-
And I realize you guys don't realize it, but I got a motor running right here, and it fills up my ear.
Okay, I realize you're really putting a lot of emphasis on the type curve.
No, there's the same amount of marks for perm, skin, P sub D match, T sub D match, radius of investigation, equally. Equally.
Okay. The piece of D and the reason why I'm raising this question is because my pen and your skin, and your pen and your skin match exactly my pen and my skin. But I realize my piece of D and piece of D actually I didn't save my spreadsheet to reflect that. I later realized that much later. So definitely my piece of D and piece of D, they're all out of point. And you're saying everything had equal mark distributed. You're saying,
If you got your perm and skin right, you would have gotten full marks for those two. If you got your P sub D multiplier wrong, if your P sub D,
yeah,
you wouldn't have gotten good marks there, and same with your T sub D. So you could have missed 2/5 of the credit on the type curve. 6. I think there's basically 6 for most of them, and then for Billups there's P star also.
so how many percentage? Let's assume I got the type curve values wrong, totally wrong, but I got the pen and the skin right. Then how many percentage does this type curve
You should,
take?
a third. If there's 6, look at your test. How many line items were there on the first question? 5. So there was no radius of investigation?
Yeah, it was. Yes, there was.
Perm, skin,
There was no
radius
P
of
star. There was no P
investigation,
star.
and T sub D and P sub D match. So you lost 2/5 if you didn't get your type curve right.
And that applies to all 3 questions.
Yes.
Thank you.
Okay. Now, it seems moot that if you already had the answers, why do the type curve? And it's because we don't always have specialized plots that we can work with. Sometimes the only way we can get the solution is with a type curve. So I want us to be able to do this problem. I would like you to be able to get perm. Now in this problem we don't have wellbore storage, but if we had wellbore storage you should have been able to get T sub D over C sub D and actually skin. I want you to be able to work that way by being able to get a type curve match and get permeability and skin as if there was no specialized plot whatsoever. Because in some applications we don't have specialized plots. The type curve is all we got. So that's why it's not a moot point, even though it appears to be. I'm trying to train you up for type curves. Yes?
You were earlier. What exactly you talked about? Your early time slope that you had.
The early time slope would have been any data. We don't have it,
Right.
okay? It would be pressure versus time. If that's a straight line, then the log of delta pressure versus delta time will be unit slope on the log data. And that automatically gets us on our type curve.
Okay.
Now, as I said, I had my spreadsheet set up as a template as if I was going to be able to calculate it. So I just guessed that number. But I didn't have to work it that way. I could have just guessed the T sub D multiplier
Right.
directly.
Okay.
So either way you would have done it, you would have gotten some T sub D multiplier.
Right.
Whether it's calculated from a guessed unit slope or it's just guessed directly.
Okay.
But in either way, that multiplier should match a multiplier that I use so that I can get that good of a match.
Okay. And now I guess my other question is, and I may just be wrong on this, our perm is obviously going to come from our slope that we find.
Yes.
Now, is it wrong to say that the slope can be, that there could be some judgment in, I mean,
It's not an eyeball fit in these problems, it's a regression analysis. It's pretty hard to...
right, but, I mean, and maybe it could be something I can show you later. Like my perm's close, it's right, it's like 1.139, but obviously,
You might not have missed any points for a 139 versus a 124.
okay.
Yeah.
Okay.
I can't
But
promise
just-
you.
But just in general, like I said, because obviously in Project Eval also, I sort of feel this way that, you know, when we plot our data and then we make our 2 points and sort of get a line, can we not say, I mean, there can slightly be a little bit
I would say, okay, tying together project evaluation, because
Sorry.
no one else is in here in my project evaluation. We're looking at transient rate data, which is extremely noisy.
Okay.
Transient pressure analysis, especially like on a buildup, is very smooth and monotone. And in this textbook cases, they're not even real world cases, they're generated by a numerical simulator. So we do tend in transient pressure analysis to get exactly some line. Where in transient rate analysis, we do kind of an eyeball fit.
Okay.
Okay, there is a big difference in those two.
Okay.
And they'll see it because when we get to chapter 9, we will do some analysis like we've been doing in project evaluation.
Okay. Okay.
And the type curve, again, has its validity because even if you didn't get a type curve match, you'd be able to pick which data points you would use for your regression analysis for your slope.
Okay. Okay.
So yeah, that's why.
Okay.
And even if you added 1 or 2 points or subtracted 1 or 2 points for when it humps over and curves in, you're not going to change the regression because look, there's like 20 data points on there. It's be really hard.
Right.
You should be able to nail that 0.124.
Okay.
And if you're not, what I think you should do is keep working these things until you're matching. You should be adjusting because you don't want to get this wrong again.
Right, and
I think that's where everybody is. They don't want to get it wrong
What you have
again.
to work on is I'm sure once again, it'd be nice to see where I missed my point.
Yeah.
Because I bet most of mine came from the type curve, because
Yeah.
it just seemed like that's where I had most, I myself just couldn't get
Yeah.
things to match up good, and maybe it was the points I was
Yeah.
picking were wrong,
But you have to admit, I can see from here that even my
Yeah.
derivative data points sit on a single dash line.
right.
Where if I move that to the right or to the left, they will no longer sit
Okay.
on one line.
Okay.
So it is possible to get the complete answer set from a type curve match.
Like in the 6.1 example, this is the drawdown case, and we need to find the T sub D and P sub D, the wedge points from the type curve. And for T sub D, it is being multiplied by the multiplier with the pseudo time for the drawdown, pseudo TA.
Yes.
But in this 6.4 example, the TA was not in the VB. The TA was given after that, So,
I've never used the textbook's T sub A. I've always calculated it. We've never used any PAs or TAs from the textbook. We calculated.
yeah, we calculated, but that was in your VB, in the bug.
Yeah.
But till that, exam, in the VB there was only pseudo TA for the builder, not for the drawdown.
Are you telling me that right now as a class you don't have 2 pseudo times?
No, but after that, pseudo TA for the drawdown was given by you in the VB after the test.
We added it.
No,
I obviously gave one after the other one, but many of the students had pseudo time on this builder. The only difference is it's the same function. You could have used the drawdown one.
I use the drawdown one.
Yeah. If you use the drawdown one, you should have gotten the right slope, because all it does is calculate what some arbitrary viscosity and compressibility to multiply it so it looks like it has units of time. And even if it is at some arbitrary pressure, if you're doing a buildup, it'd be at PWF instead of PI. See, the drawdown pseudo time was such that you're assuming you're drawing it down from P average, and so it used that. It shouldn't affect your perm. If you use pseudo time drawdown instead of pseudo time buildup, the only thing is your viscosity compressibility that it moved it back would have been an arbitrary shift that could not affect your slope. You should still been able to get exactly the same slope.
I tried then to get wrong, but there was a slight difference, not that bad.
Okay. Do you have the buildup pseudo time now?
Yeah.
Okay.
I have both now.
Okay.
Do you have the statistics of the grades and distribution or anything?
Yeah, but I can't show them because I show everybody's.
Oh, okay.
Yeah, that's what I'm saying. That's why I made a note.
Right.
I
I mean,
can.
I'm sorry, as a class. Like what the average of the class was. the
Yeah, he
low,
sent
the
that. He
high.
sent that out.
Oh, you did?
Yeah.
Yeah, it's on D2L.
Okay.
Did I do it for the total grades or did I break down by question?
Total.
It was total for both tests.
Yeah.
It was the average for
Yeah.
both tests.
It was just where you sit in the, where you compare to your friends. Okay, that was 6-1. Okay, so 6-2 was a buildup. And again, this annotation shows the entire results. Pseudo pressure versus Horner time, where your delta T is a pseudo time. And of course, on a Horner plot, your P sub 1 hour has to be calculated. It's a function of T sub P. So where you get your pseudo pressure at 1 hour for your skin equation is not going to be as simple as it is in a drawdown. You have to calculate Horner time at 1 hour. Seems to me, Grady, that I had some point to make on that I didn't, but we'll get to that. Okay, now the additional thing we can get on any buildup, whether it be radial flow or linear flow, is we can get an extrapolation, because Horner time is constructed so that at infinite shut-in time, the ratio becomes 1, so we can extrapolate the linear section to a P star. And I think almost everybody got full credit for P stars. It seems like everybody was really good at that. And selection of the proper straight line, I got a perm of 1.005, which tells me that they probably used a simulation perm of 1. And I got a relatively high skin, 5.5. And again, I'm coloring in my radius of investigation because I'm using my oh, that's the point I wanted to make. I think that we do not have, and the textbook does not tell whether we should use actual time or pseudo time for when we plug it into our radius of investigation. We should use pseudo time. It doesn't have that much of an effect, and I don't think it affects anybody's grade, but when I was grading, I noticed some people use the actual time that they used of the last one, and some people use the pseudo time corresponding to that last time. It shouldn't have affected anybody's grade. I was cognizant of that, and I realized I did not in class talk about that. But we should use the viscosity compressibility normalized pseudo time. Because there's a viscosity compressibility term in that equation.
But do you mean the 30A or what?
Pardon?
The pseudo-time you're using not 30 but 30A, right? Or
The pseudo time that's used to calculate a radius of investigation of 411 feet
yeah, I mean
is,
which one?
well, I got the old-fashioned one. This is when I used to use tables. Would be 300, yeah, don't quote me on this because I don't know if oh, here it is. I can actually delete that. Here's my,
Man, it makes quite a big difference in mine.
Yeah. I mean,
Okay.
I use 30 or probably
yeah,
don't
it's,
have to.
instead of using 169, you should use 220.
220.
334.
334?
It's 334.
This is a build-up prompting for time, pressure, gravity, reservoir temperature, and no impurities. Does this have 8% H2S?
Yeah.
Yeah.
Okay. And 3,500 was my initial pressure? Yeah.
35 initially, but after
Okay, and that should have been verified by our P star, except for I've got a P star. Let's walk through this. I may have made a mistake. Did they give us 3,500 as initial pressure?
Yeah.
But we only get a P star of 2273.
2273, yeah.
I've done it with both, I've done it, looks like several ways here.
And then
Which one's the right way? Yeah, here it is with pseudo time. Let me double check my slope. Because last year I didn't have a VB function. Oh, I see, it's on my, I'm gonna have to check, make sure I got everything here right. Our Horner time, yeah. I'm using my calculator. This, I should be able to get rid of this column right here and not have it affect anything. Good. You'll get different numbers. I can see the point here. If you
It's not the
change,
same, no?
if you change this to 2273,
that's right, yeah.
Yeah, that's what I did.
I think
That's what I did.
Because that's what we did in class.
yeah, that's what we did in class. So
Yeah.
we changed that to 2273, and then of course we get a different number, right?
Yeah.
So then we changed this one more time to 2271.
So it was 72.
Yeah, 2272.
Yeah, 272.
I was gonna say, I wasn't sure if I did that
Yeah.
right, 'cause I think we had. I
Yeah,
had
I think
3,500.
Now-
guys.
Now, how does that affect our radius of investigation? Does anybody remember where I started? 4 something?
Using pseudo time?
Well, now my pseudo.
You said
time-
411,
Let's just see what I got here. Radius of investigation,
but now if I use pseudo time, I get like 570.
I get 576, but why am I not annotating that on mine? Okay, yeah, it should be 576 using pseudo time. Okay, and I've dropped my perm to 0.997, 2271. Skin is now 5.2. I can tell you right now, this is not going to change anybody's grade. These are all within. These things were pretty wide for radius of investigation and for P sub D and T sub D multipliers. But I was obviously working with. 'Cause this is the way we did it last year. We did it in tabular form, and this year I wrote a VB function to do that for us. So that's a better look at what the answers are now. Still, permeability is 1 millidarcy skin. If there would have been no marks taken off for a skin of 5.2 versus 5.4.
What about 4.5?
Huh?
What is 4.5, 4.6?
Again, 4.6 for skin.
Yeah.
You would have probably only gotten a 4 out of 5, but don't quote me on that. I will give you the marks, and we can then you'll know. I'll strip out from my two-dimensional spreadsheet that has everybody's name. And I've got your marks by each item, and I'm derelict in my duty for not having done that before class. That's the trouble. That's the trouble I get in working it both ways. See, I was trying to get it, but you can see there's hardly any effect. This should be no, because I didn't run. None of this stuff should be used. Okay. So then we move on to our type curve. And I can see right now that, I don't know what I did different here, but my type curve now looks like it's a little off. What have I changed my initial pressure. And this is but this is a situation where I did, yeah. Let's see if I have a unit slope straight. How come it doesn't ask? Oh, I know it doesn't ask you to reset. Where is my pressure time data? My derivative looks good. It looks like it's all calculated. T sub D coefficient. Let's look around here. 212, 88 feet, rate. Here's my early
I don't know
time.
what you're asking.
And it was a guess on that, so I'm using the same technique I used before. Let's see if I don't get a slightly different guess. Because after I changed initial pressure. But I'm telling you, the range I made on these T sub Ds and P sub D matches were pretty great. So I would actually make this a little bit smaller. And I've never seen this tail up on an actual buildup before.
You know, of course, not saying I did it right or anything, but I had on this same problem, I had it comes down, it tails up exactly like
Yeah.
that, and I couldn't get rid of it. I mean,
No, I'm not quite sure what is wrong with the data. But the derivative data gives me pretty good unit slopes. See, both the derivative and
right.
should be unit slope. And
Yeah, my derivative looks almost exactly like that, but yeah, I got that tail also.
Yeah, me too.
I'm trying to rematch my data, but you see right now my derivative data is crossing that one line. And again, that's why I'm going to make it bigger now, move to the right. I'd almost have to move it back to where I had it, even though my derivative data is below my unit slope and my actual data is above my unit slope. With this type of mesh right here, I'm landing my radial flow where I want to, and my red data points pretty much all fit on that line except for this early time tail. So again, work with that. That gives me multipliers for T sub D of 4.71. A lot of you are using the reciprocal. So if you're using the reciprocal, you should be looking at a number like 0.212. And my goal is to not cross different lines, especially on that derivative. Okay, so I did make some changes there because it didn't dawn on me that I didn't use my, I didn't correct my pressure.
Can I see your skin calculation?
Of course, I got in the VB function,
Uh,
but I can tell you what my variables are.
Yeah.
So here's my, let me get this out of the way. Down here, I'm using my, here, my mouse is over 1 for 1 hour. That gave me a Horner time of 7201. That's probably my P star at, or my pseudo pressure at 1 hour that I need for my skin equation. I need the perm, and I need my slope. And I can see up here that instead of using absolute value, I got a negative sign in front of W22. And then up here, I'm using my viscosity and gas compressibility. Did I give you 78% for gas saturation?
Sure.
So that's, if that helps you.
What was your PWF value?
It looks like it's, or my PWF on a buildup would be my 0 point. At 0 point, remember I keep drawing this graph. On a buildup, we're drawing down, then building up. So this is your PWF.
What I use is, I don't know where I'm off.
So my pressure, my first shut-in pressure is also my last flowing pressure. So my pseudo pressure corresponding that is that number right there, 302.
I want to make sure I'm using the right numbers. I just don't know.
I definitely recommend you spend some time massaging your spreadsheet to match these numbers.
Thank you.
The last one. Looks like I got a little bit of
Is this somewhere that we can see it? Or the numbers at least?
I've scanned over like I did for Gene, all the numbers.
Okay.
And I recommend you work with other students. Why do I have two things? Oh, on this one, I'm going to copy paste it so I don't lose it. But for display purposes, there's no reason to put in what the textbook had there. Here would be, now, I think exercise 6.3 was using a bottom hole shut-in device to minimize the effects of wellbore storage, and so you had very little data early on that would have reflected any wellbore storage. But this graph right here is pretty much the results. Again, I colored in my last data point because it's still on the line. I can't emphasize that point enough. I do not use the last point on my line I do not use the last point measured if it's not on my line for the radius of investigation. Because if the data deviates from that, I'm no longer investigating more and more reservoir. I'm showing a boundary. Now, these three problems all happen to still be infinite acting radial flow, so I always use the last data point, but beware, we don't always use the last data point for a radius of investigation. Now, I seem to have gotten this one right. I'm using P star 2702, feeding it back into my initial pressure to get my fluid properties. And radius of investigation, let's see if I did this right. As far as which time I use. Uh, 967 E1. Oh, that's because I ran a maximum. That's why I was in E1. And I definitely used it off my apparent pseudo time. This is just a max function that picks up my last time. Okay, and did you have to calculate T sub P star on this one, right? From the cumulative production to the last rate. That was covered in the textbook. Final rate, cumulative production, you normally do that division to get your T sub P star when you don't have an actual time produced. When a well is produced at constant bottom hole pressure. Standard procedure. And then finally, here it is again, early time slope. It was trial and error. Let's move it down. Well, let's move it right here. Let's try to move it here. And it's hard to get, and I got a little bit of tail up here, but not significant enough to convince me I had a boundary. But all my red data points are on one line. And I mean, I could move that to the right a little bit. I could make this maybe a little bit bigger. But then I'd lose a lot of, I could also make I could move a little bit bigger, improve my red data points, and I could make it a little bit smaller and improve my derivative. Coming way back to here, actually improves my derivative, but you can see how my red data points now traverse 2 or 3 lines. So it's a combination of fitting both the pressure data and the pressure derivative data to try to get the very best match you can. Gotcha.
I just want to make sure I understand this, because on some of my work I use the regular time to do the radius of investigation, and not the apparent time. So
You would have lost very little on marks.
I'm just asking.
For the future, what's...
In the future, we should use pseudo time.
We should always use.
Yes.
I just want to make sure, because on some of my old spreadsheets, it doesn't make a big difference if the times are, real close, but like on this one, it makes a huge difference in the radius.
Yeah. Let's try to explain why we use pseudo time. It's equation 612A. I want to stay here. But in our textbook, in that equation, is viscosity and compressibility. Think about it this way. Let's say we used not apparent pseudotime, but pseudotime. We did not multiply back in by compressibility and viscosity at initial pressure. Then we could actually take out compressibility and viscosity from the form of the equation in there. So it's really 5 mu c sub t, and the mu c sub t has to be normalized. So, and I realized I did not make that point during the lectures when I started grading, because sometimes until I started grading, I realized that half the class is doing it one way and half the class is doing it the other way, and I realized I didn't go over it. But really, probably no marks were taken off because you used one or the other. It's only when
I'm
you
just
didn't.
asking, because on 6.2, there's like 10 difference, and then on this one, it makes like 500 difference. So I just wanted to make sure.
Okay, from now on, it's always pseudo time for our radius of investigation. Yes?
What's your scheme for this? And,
My skin was huge, 11.47.
okay, I just have one question. How do you, for the early time, for the slope to calculate the skin and permeability stuff, what kind of data you choose? Like,
Well, the data I chose is exhibited on this red line. I used all the later data points up until it looks like right about here where my cursor is. Those would be the data points. Because that red line is going right through the middle of that data point, and then it's starting to tail away from there on out.
Now, obviously, sort of going back to, like I said, I'm not worried about points because you said you gave us a window and all. But would you agree that like something like there is slightly subjective as to which sort of data point?
Yeah.
I get what you're saying. You can look at it and say it goes right through, and I completely understand this isn't an argument. I'm just saying for future when, you know, if you were to do this problem and I was to do this problem, would most likely come up with slightly different answers every time?
Less than 1%.
Okay.
Less than
Okay.
1%.
Okay.
Because if I look at my type curve, I'm not going to use this first data point, am I?
No. Okay.
I'm not going to use this second data point, am I?
Okay.
Or the third. And you know what? If I use or don't use the fourth and fifth, because there's so many data points,
Okay.
you can't get a different slope.
Okay. I got it.
You see, yeah, it's basically if I average these points or these points plus that one or these points plus that one.
Right. Okay.
You
Okay.
really can't get a different answer.
Okay.
Okay. And which one did I change my answers on? The one with the, was that 6.2 that I changed? No. Or, yeah, this is what, yeah. 6.2, new key, PI.
I'm sorry, what was the multipliers on 6.3?
Okay, yeah, I didn't go over those. What past? It ended up to be 113.44. A lot of you are using the reciprocal of that. I'd get 0.0088.
I didn't hear if you addressed this or not. Did you match your PI with your P star?
On this one,
Yeah.
on 6.3, 2702, it looks like I did. 2702.
Okay.
it doesn't change the perm. The perm is the holy grail.
Mhm.
That's what we're primarily after, is permeability. We can basically tell you whether a well is commercial or not if we know its permeability. That's the big driving factor. We can do the skin. The perm is very important to the reservoir engineer. The skin, depending on, in the old school we used to call them production engineers, but now they break that out and call them completion engineers. But if you got a high positive skin, that's important for the completion engineer to know. Maybe he just doesn't have enough holes in his pipe. Okay, because we're talking about a vertical well, radial flow. Maybe just things like phase angle and the way they perforate, the number of shots, perforations per foot, or oftentimes there's a problem with depth corrections, and they perf the wrong thing. If you got stringers and you're off a little bit, and you just don't get enough perfs in the actual pay zone, it'll show up as a large skin. It's a mechanical skin. It's not the skin that we showed in class where we have a mud invaded.
Yeah, it's not a damaged skin.
Yeah.
So.
It's not a damaged skin, but it'll show up as a high positive skin. I've seen ridiculously high skins, but typically it's some combination of formation damage, mechanical damage due to perforating the wrong zone, things like that.
Yeah, at one point I remember you had mentioned partial penetration, so that you're getting like hemispherical flow or something like that. That could show up as a skin.
Oh, yes, and now I know what you're talking about. Let's say you've got a thick zone here, but you only drill this deep into it.
Yeah.
For some reason you stop drilling, then when you drill, it's going to tell you got a lot of perm out there, but you don't really have access to it, as if you would drill all the way through it. That's called a partial penetration skin. So yeah, they're in the production engineering book we use in our undergraduate. They have like 7 or 8 skins that could contribute. Yeah, slant. You can get negative skin by, instead of drilling a vertical well, drilling a slant, because you see you're exposing your well bore to more pay. Just like the extreme case is a horizontal well, but you don't calculate the skin on horizontal wells. Okay, are we done with this spreadsheet? We want to get to that one next. Let's go back here.
Sorry, one last question. For the last 6.3, for the honor time, you use the actual time, you use the production time, or the one that...
The TCP star, was that the TCP star? Cumulative production divided by the last production rate?
Yeah. Well, for the constant, I mean, there is a constant...
Oh, the multiplier? I have to open it back up.
Sorry. I think I have some problem with the honor time calculations. I want to make sure.
Okay, are you talking about the type curve or Horner time?
Honor time.
Okay.
6.3, yeah. Or you don't have
This looks like my Horner time right here.
Okay, can see the F3.
So I'm using 2237. Where am I getting that from?
Okay.
That's 24 times, yeah, my TCP star was in days, 93.
Okay. So
And then I had to multiply it by 24. I'm glad you asked the question to get it in hours, because my time is in hours, and I'm doing that ratio, so they have to be dimensionally correct.
So we must use the what I call the real production time, not
Yeah.
the actual time, right?
Clearly states in our textbook that we always use the actual time for the production time. There's no pseudo time, production time. We don't have a pressure measurement to do anything with it. Yeah.
Why did you have 93 days instead of 91 days?
Did I do it wrong?
91 days are given in the example. 93 days.
I got cumulative production of 76272 divided by 818.
That's the equation I give in TP.
They call it TP star.
Yeah, they give the equation, which is
Cumulative production divided by last final rate. When a well has been producing at constant bottom hole pressure. If you have a lot of fluctuations in your rate, you really need to use superposition like we did on our very first problem.
I'm still a little bit confused. Because you just said we have to use the actual time of production, right?
Oh, I thought you were, we don't know what that is.
It says produced for 91 days.
Oh, no. But weren't we given the cumulative production? And weren't we told that it was produced at constant bottom hole pressure?
Yes.
At constant bottom hole pressure.
Uh-huh.
When you produce a well at constant bottom hole pressure, T sub P star, which is what we use instead of T sub P, it's an attempt at superposition. It's allowing for the fact that we didn't always produce at that last final rate.
Okay, I found a place in the book, like during the test, it says literally, for Horner analysis of a build-up test following constant pressure production, you use the actual time.
Yeah.
Actual time.
500, it's 504. I don't know whether it's correct.
what time did you use?
I use 91 days.
You have to convert it to hours, right?
Yeah, I converted it to hours, but I use 91 days.
Okay.
How many hours did you use?
2,184 hours.
Okay, let's look at the effect that would have. I can do it all right here, right? Here's our perm. And here's our skin. Now, we're not going to select any different data. So if I change this from 93 to 91, my perm goes from 743 to 742.
Okay.
My skin, I've got it now at 1145, 1147.
Okay.
Nada. But I will double check. If the textbook says, I need to look at the section where it introduces T sub P
Oh,
star.
I can give you the reference because I put it in my
Well,
spreadsheet.
I need to know. I'm sure that we normally, I mean, why would they give us the formula for T sub P star if they didn't tell us how to use it?
Right.
Okay. I'll have these answers by next week. Okay, now are we done with this spreadsheet? Okay, we just got one small thing to clean up on example 6.8 that we almost totally completed in class, but we were having a little bit of function. And if you guys stayed a little bit longer, you'll find out that I think there's a typo in the book that it's not 168 hours they produce, it's 168 days. And so if you say it's 24 times 168, or a T sub P of 4,032, then voila, it looks like your data falls very nicely on the Bennett type curve for constant rate, which is a buildup. And you don't have that tail on the end. So some of you stayed late and catch that. What I did the last minute is I opened up last year's spreadsheet, and sure enough, when I went back to my office, I saw that I corrected my book. It's hard to correct my PDF version, so when I keep pulling up the PDF, I don't see the mistakes that I've already found. Now, another thing, because we're going to use this sister of this type curve tonight. This is the constant rate which we use for buildups. So that means the pressure is varying. There's the constant pressure type curve, which means the rates varying for a drawdown. And we need to go over what these symbols mean. The important ones are the X's. And the most important is the first X, the one on the left. And as you see, as you move down the family of finite conductivity vertical fractures to the lowest one, the highest conductivity, or near infinite, the X's have a bigger bandwidth. You see at the top, type curve, the bandwidth for the double X's is very short. That's the amount of time in this idealized reservoir that you'll be in linear flow. And also important is the time that linear flow starts. So just like we use the radial type curve to determine when we could use which data to select on our specialized plot, this aids us in selecting data that we would use on our specialized plot. So there's actually not an, yeah, there is.
So are you saying those X's form like a cone on this?
A bandwidth.
Yeah, okay.
Okay, from the beginning to the end, each line pretty much has an X on it, or you may have to interpolate.
It's two X's.
Two X's.
Yeah.
Okay, data between those two X's should be in linear flow,
Okay.
which means we can use that data on the specialized plot. Okay, so for our case, would we use data points 1, 2, and 3? Okay, now let's check that out. Didn't we do a specialized plot?
You mean the MC?
Oh, I see what you're saying. Okay.
And also, when I changed my T sub P, see, I'm totally different here. Remember how I had two distinct straight lines before? So isn't this, this doesn't look like it. I borrowed this graph. This was done in quick order here. So the specialized plots would be either the MC or the square root of time plot. As long as we're within 10% of our produced time, we don't have to apply any superposition. And now that I've just increased my T sub P by multiplying it by 24, in order to get, I should just be able to multiply, I should be able to cross-plot the square root of my pseudo time with my pseudo pressure and get an early time straight line, but omit the first 3 points. Let's see if we can do that. Again, I don't know what this graph originally was.
We did an MC plot.
Okay. But the thing I like about the MC plot is it also gives me my extrapolated pressure. Let's just go, with that in mind, let's just work with that. But I'm gonna, although I'm not gonna run this all the way to 0, I'm still gonna get the right slope if I expand this and make my min 40. And then I gotta get this graph quite a bit smaller so I can fit it on my screen. And my annotation's totally incorrect. This is delta pseudo pressure. Oops. Let me try to correct this. Or maybe it's just pseudo pressure. Maybe I didn't-
Yeah, it's just pseudo pressure.
Okay. That's pseudo pressure, and this is, let's just call it TA, right? Let's do it both ways. Let's just take the time. We're going to do it versus the square root of TA. That's not what I got plotted right now. Let's just use it versus the square root of TA. And now I've got to change my y-axis completely. My x-axis.
Did you copy the MC plot?
I should have copied.
Or you just modified the MC?
I modified.
Okay.
I should have copied it because now I'm going to, in fact, now that's exactly what I'm going to do. I'm going to copy it first. What I want to do is show you that we're going to get the same slope.
Okay, so you're doing the same graph, but just as a function of
time.
Square root of TA.
Yes, I'm going to make it the square root of TA. How come that's saying it's odd? This something is not working here. See, it's reading 40 to 80, and this thing is saying 0 to 20. Why is that doing that? I can't even change it. It's like it's, oh, there we go. I got it to change. But let's make it 10. We're interested in our early time slice. So let's go back and look at our type curve. We decided, as far as the x's are concerned, see this, that I should not use the first 3 data points. They're not in linear flow. Then I can use the 4th, 5th, 6th, and 7th. You see that? And then I pass the x and I'm out of linear flow.
Can you come again with that, please?
Go over that one more time.
Yeah.
The type curve is telling me which data to use. Now, I couldn't even make this type curve until I did my specialized analysis, got a square root of kxf,
Yeah.
plugged in
That's
my
what's supposed to be.
0.1 and got an x sub f, and then I could calculate t sub dxf. I couldn't even get on this plot until I was done.
So we're just correcting. what
Now we're cycling through,
Right.
okay? And this is why we use the type curve. Just like I said earlier, sometimes it's the only thing we got because we don't have a specialized plot. But in this case, we're going to use it to recheck our data. I can tell this is a simulation, but I should use not the first, second, and third data points because they're before the x. I should use the 4th, 5th, 6th, and 7th data point, but then I run into the x on the other side. So let's highlight 4 through 7 on my t sub a.
Data between the 2x point is a linear flow.
4, 5, 6, and 7. That's the data that I should try to calculate a slope with to get my square root of kxf, which will result in my frac length. Okay, so I'm going to get a different answer here, but let's check. So right now, I am calculating the square root of kxf based on some slope. This slope is from my MC plot, but right here, it's absolute, isn't it? I'm going to copy it over to this cell. Should be the same number, but now I'm going to edit where I'm grabbing the data from. I am not going to use the MC data. I am going to use the TA data. I'm not going to use all the TA data because I decided the first 3 data points shouldn't be on there, right? Everybody with me on what I did? Just for comparison. Well, I got a drastically different number, didn't I? 1 million versus 5 million? Oh, I need to use the square root of TA. Okay, now I get 4.5 million instead of 4.8 million. See that? Although now I should also look at adjusting my data selection on my MC data. I'm just using 4 through 7. And these numbers should be very close to each other. 4.7 versus 4.5. Now, I like the second number better. And I'll tell you why is the first number is depending on what?
MC.
Pardon?
MC.
Yeah, but what's the difference between these two plots? What additional factor is in the MC plot? Time, the time produced, okay? So, as we know, we've had an argument earlier about whether we should use T sub P star. It's not, okay. A buildup, if you're going to use T sub P, has to be produced at exactly constant rate and then build up, okay? Now, we really hardly ever know that in the oil field. We hardly ever produce well at constant rate. Exactly. Now, but because T sub P is really large now, here, I'll show you how large it is. Because we multiplied it, you know, it wasn't really that big, but now it's really big. Because we multiplied it by 24. So 10% of that is 40 hours. No, it's 400 hours. And I'm only looking at 11 hours. I'm actually more comfortable taking the slope I'm getting from the square root of T sub A than with the MC plot. Because with the MC plot, I've thrown another parameter in there that is unnecessary. Now, I like the MC plot because that's the only thing that's going to give me P star. My extrapolated pressure. For actually calculating the permeability, I mean the permeability was given, but using the square root of KXF to get X of F, I would rather use the 4.5 rather than the 4.7. So right now I've got an X of F of 225, and that's going to bring it up to 234. If I was running analysis on this test, that's the way I would go. I'm more confident, especially now that I've really increased my T sub P, that my early time data does not need any superposition. Does not. It's going to be a pure drawdown data plot.
As regards your second slope, how did you said something about squaring something?
The first time I did it incorrectly. I used T. It's got to be the square root of T.
Okay.
And hopefully that's what I got plotted here too. Yeah, I got the square root of T. T sub A. So that's my best number for X sub F. Square root of K X sub F is just fluid properties. Fluid properties are at a known initial pressure and are given perm. Now, I still like the intercept. Okay, I'm not done with my intercept here. Do you see this? I've just changed my slope. Remember? I've just changed my slope on my MC plot so that it's only the 4th to the 7th point, right? Now, I haven't done that yet for my intercept. Remember, the way I do this quickly is now that I have that data set, then I just change the word slope to intercept. And what I had before. I had 5421. And I brought it down to 5396, a little bit closer to the reported initial 5,000. And how does that look like on my, I'm going to reset this to 0. Not
So
necessarily.
you're using how many data points?
Just 4 points, 4 through 7. 4, 5, 6, and 7. And now,
The 7th one's kind of iffy, isn't it?
well, now that we've cycled around, maybe we've changed our data a little bit. The fourth one I'm good with. It's after the X. 5, 6, 7 is good. You see, then the X occurs. 4 through 7 are solidly on my data, within my data set.
So does the data prior to the first X show the variable storage?
Not in this case. You notice all the data is on this graph, or is on that line. So that line is no wellbore storage effects. You rarely see wellbore storage in a fractured well because it's like a negative spin. It overwhelms. There's so much easy flow into the wellbore. Think of it this way. If you just have like radial flow and you got some perforations and you shut in the well at the surface, it takes a long time for it to fill that up. But with a stimulated well, the amount of gas that can come in immediately after you shut in the surface, it happens real quick. But there's no deviation. The reason it's not on linear flow is that it's in bilinear flow. Okay, so that's where the squares come in on this graph.
One question.
Yes.
What if for certain analysis of data we got a plot in between the lines? Then in that scenario, how do we select the
Interpolation. Okay, so let me do that. Let's do that right now. Insert. All right, you gotta help me find shapes again. Here it is. And then I want a squiggly line here. Okay, so I don't want that. Insert. Here, I think I want this. Okay, I'm just doing the first one, okay? Okay, I've just done it. That's how you'd interpolate. That's the beginning of linear flow. On this graph, there's actually 3 flow regimes exhibited. Bilinear flow. The bilinear flow is the squares. And the bilinear flow period ends, or is the same as the axis, is between the boxes. And this is a little strange, but the length of the bilinear flow has a maximum in this mid-range. So for our example, we should have 1, 2, 3, 4 data points, our first 4 data points, because that one can be shared by either flow regime, would be in bilinear flow. So there's data that are on these curves is bilinear flow, linear flow, tailing into radial flow. Okay? Now let's look at the green garden type curve.
So, what would be your basis for ultimate decision making for identifying the linear flow? Will it be depth chart, that type curve, or we can use on our own choice like MC plot or the type curve? Or this is the best way for identifying the data range for linear flow?
I pretty much use these 2 type curves anytime I'm looking at linear flow drawdown or buildup. Okay? So this one is more explicit. I'm just tired of these markers, so I'm playing here. I don't like, I only use those for auxiliary. Fill, solid fill. Where's the colors red? And I think they're too big. Okay. Now they look the same as this one. Okay, so keep in your mind the only line that's on the graph on the left is the bottom line on the right. Okay? The green garden type curves for infinite conductivity vertical fracs. The only infinite conductivity vertical frac we have here is the one that's 500. 500 is about the same. Okay, so our data is slightly above it. Well, look over here. My data is slightly above it. I can live with that. I'm not trying to match that because I'm convinced at this point in time my conductivity is 25. See that? So the Bennett type curve is extremely helpful to me in this case because I do have a finite conductivity fracture, and in the real world most of the fractures are finite conductivity. So that's extremely helpful there. The green garden type curve truncates my data. I can't even get all the data on there. But it does tell me basically the same thing. It tells me the first, second from the tail end, third, fourth, fifth, sixth, seventh point should not be included. Let's count backwards from here. 1, 2, 3, 4, 5, 6, 7. Now, they're telling me that I shouldn't use those 7 points on the green garden type curve, but the Bennett type curve says I should not only use those 7, but I shouldn't use the next one either. And that's because it's acknowledging that I have a finite conductivity vertical fracture, and the solution for when my linear flow regime ends is different for finite conductivities than for infinite conductivities. The thing I like about the green garden type curve, it shows to me what happens if I go into radial flow. But in most cases I don't. I kick up into boundary dominated flow. Your question?
Prior to plotting the data on both the curves and then figuring out whether the structure is finite conductivity or infinite, can we do this before plotting the data on these curves? Is there any method rather than doing the plotting on both the curves and then identifying?
Let me answer your question in a roundabout way. Let's say we were back in radial flow. Knowing everything I know right now, the first thing I would do is calculate the pressure derivative. And if it's flat, then I'd make my specialized data from that flat data. And I'm basically done. Okay? On linear flow, I actually have a derivative. So let's go there. Now, you notice that we're still using... I'm glad you asked that question. Because we can do the same thing. We have already calculated a pressure derivative over here. And it wasn't very conclusive. I think these are both half slopes. I've changed the data a little bit. And if I was just to base it on half slope information, let's get rid of this box right here. If I was to base this on this plot right here, remembering these are actually radial derivatives, it would tell me that all my latter data points should be not my early time data, but my later time data. It doesn't do a good job of picking out that middle section at all, does it? There is actually a linear derivative, and this really didn't come out to the literature until after our book was published. It came out in the work of with DFITs, diagnostic fracture injection test. And I think I have it memorized. So let's do another separate derivative. And I'm going to insert a row in my spreadsheet and call this radial, right? That derivative was developed for radial flow. It gives us a flat line when we have radial flow. Let's do the linear derivative. What do we got here? I don't like the way this is all spelled. I don't know why. This must be left over from my very first problem where I allowed myself to use apparent pressure. I believe it is 1 over the square square root of t dt dp dt. Boy, it's not that hard. Okay, let's calculate. Keeping in mind that we can only calculate a derivative, or what we standard procedure for this class, knowing that we're using synthetic data, is to gap it here. So equals 1 over the square root of t. We have the square root of t. It's right here. Times dp, dealt with pseudo pressure for us. Are we running a build-up? Yes. Divided by delta t. And I don't think I did something right here, because this shouldn't look like this. I should show a constant. Okay, let me find the source. Probably fastest for me to go back to my office and get the source.
Would be a good time for a break.
Let's take a break. I'll go to my office, get the source. It's recording. Okay, so I didn't have it memorized quite right. The square root of time goes upstairs. So all I have to do is get rid of this 1 divide. And my data 4 through 7 should be fairly constant. And it's hard to tell looking at a table of numbers. But let's put this on a type curve. Let's put this on the Green-Garden type curve. No, because it won't, the Green-Garden type curve doesn't have enough. We'll put it on my Bennett type curve. So I'm going to copy paste. I'm going to have to make some adjustments here. My linear derivative. I'm going to copy, paste, it won't appear. And then I'm going to select data. That doesn't work. I have to, I've got to put it in a legend just to access my data. Series 3. Format series. We're on the secondary axis. And just in case I need that again. It doesn't matter whether I use log or not, but how come I don't have it on my data now that I've got it put on my secondary axis? Oh, I know it's, well, let's see. I got to make some select format data series. Okay, when I format data, oh, see, it's, I know, I have to rewrite the x data here. I know what I'm doing now. I could have done this a little bit easier. My x data from my linear derivative that I copied in here, this data would be my T sub d x of f data. I'm guessing I'm getting it. I can't see.
Where do we get the linear derivative from?
It's an equation they put on the board.
Let's see if I've got everything right now. I don't have everything
Let me
right
get
now.
that secondary x.
I want to put the T sub dx right here. Okay.
I'm putting on.
And it's a really wide scale here, so let me,
I'm sorry, how'd you get that secondary axis again? I'm sorry.
with great difficulty. Okay, what I had to do is I had to put a legend in.
Okay.
And then, once I got the legend in, then I can select series 3. And then I can right-click and format the data series.
Okay.
And that's where I click secondary axis. Pain. Let me squinch this up just a little bit, because statisticians can do amazing things. 2e to the 6. Actually, I did just the opposite of what I wanted to do. Let's make my max double what it is. Yeah, now it's working for me pretty well. Okay, now let's give it some color. Format data series. Let's make their guts yellow. And let's make its marker color. Where's my marker? Marker options, build in. Where's my marker line color? Border, solid line. There we go. Now they stand out. Okay, so I got a little bit of an S curve here. You see this on my derivative? Now I've got it on my type curve. The x-axis is right. It's the same T sub d x sub f that I've calculated. But I don't have it in a P sub d format yet, a P sub d prime format. Although I think I'm ready to do that. Let's see here.
Can you click on the linear derivative real quick?
Square root of time is an E12. It's upstairs. Times D, and of course in our case we're doing D pseudopressures, is M of P C13 minus C11. And my delta T is my delta TA, which is D13 minus D11. And you really can't tell from the numbers, and I don't have, what I'd really like to see is a tail end, flat. And the only way I can make this any flatter is just keep squinching my scale. But we're kind of seeing the same thing that the x's were showing us earlier. That I like this now that I can draw. Now I know how to draw. Insert, shapes. I'm going to draw a line from, what is that? Where did that come from? Oh, it just, okay. I'm on the line that I'm on. My X starts right here, so I'm going to make this go vertical. Then I'm going to Control C, Control V. I thought Control C, Control V. I should have. Come on, do I have to draw another one of these?
It's up there on the left. It's
I got you. Now, my other X ends right here. Now, it's a little tough to tell, but do you see that I curve down, tend to flatten out, and then curve down again? That's what my X's are going to say. Now, I think my linear derivative would have been flatter in that belly if I was infinite conductivity. So it's really not, the derivative's not helping me that much, except for I didn't have to calculate my T sub D coefficient or my P sub D coefficient and look at it on a graph to see that. I could have just looked at the derivative data. Let me show you what I mean by that. Okay, I got rid of so knowing what I know now, I would say my best shot at getting a linear flow would be to try to find a flat line through my data. And you see, I would have got the middle of the data points that I got. 4, 5, 6 are my flattest derivatives right there. Okay? So just like we were looking for a flat line in our linear derivative data, this derivative, once you put your square root of time upstairs, should do exactly the same thing. It should give me a flat area, because then it's saying that that's constant, that derivative is constant. I don't know enough about it right at this point in time to tell me, but I would suspect the lower the conductivity, the more S I'd have, the less dependable this technique would be as a standalone technique to delineate which data points to use. But that may help you.
Thank you.
But on the other hand, if you just are happy to cycle through, like what we did between last class and this class, and utilize the annotation that's on the plot to tell us where to find the linear data will also be helpful.
so you wouldn't have the same problem with the other type curve, just trying to fit it, just like you did here. It wouldn't be perfect. I mean, so they're not equal. This is a lot simpler.
This is a finite conductivity vertical model, and this is a finite or infinite conductivity.
Okay.
They're different models. This one's really good for detecting the end of linear flow. It doesn't tell us anything about the beginning, because there is no beginning for infinite conductivity. It's always linear flow for infinite conductivity. There is no bilinear flow period. As you decrease the conductivity of your vertical frac, you increase the amount of time that you're in bilinear flow. And all we can say is quantitatively, no, we're going to be above that line, just like the Bennett type curve shows us. But that's the end of linear flow for infinite conductivity, where this sentence and this arrow is this last X, which I've just about completely wiped out. But it's the second X on the bottom line. That's your closest thing to infinite conductivity we have on the Bennett type curve. So that would correspond to where it says it in. What this does show, which is totally of no value, because I've said many times in this class, I've never seen a stimulated well go from linear flow to radial flow. So to me that means as you see these things fan off, they only follow the top line. They never follow the bottom line. But if they ever did, it would tell you when you could start using a semi-log analysis in your radial flow. Okay, we beat this one. Any more questions on 6.8? Okay. How many people have got a piece of paper that looks like this? Okay, so I'm going to move copy this. See where this says name? That's because there's no software, right? But when I move copy this into my other workbook at the end, I'll have some values there. See? All those values appear because those are built-in VB functions that we've been using all along. Okay, how many people have already read this problem? Okay, so this is a well that's producing at constant bottom hole pressure. This is actually a Chapter 9 problem. And we've already done a Chapter 9 problem. We've done a radial problem, right? Where a well was producing at constant bottom hole pressure. So this is a drawdown. We have rates. You see, we don't even have any pressures. We have a constant bottom hole flowing pressure of 2,400 psi. And then if you produce it at a constant bottom hole flowing pressure, your rates decline versus time. Next to positive, this is hours. Someone correct me if I'm wrong.
Seems very specific for hours. Are you sure it's not an adjusted hours?
It's hours.
It's hours. It's simulator data. So I don't know what the constraint that the modeler put in, but these were automatic.
Okay.
He didn't try to match days or hours. No, it does look very convoluted. I totally agree. So if you were doing decline curve analysis, like one person in the class has done, you'd normally just plot this data rate versus time. And usually you do a semi-log analysis when you do decline curve analysis. And now you have at least a look at what's going on. Your rate declines over time, okay? I have a problem with this problem is that it didn't tell us the gas gravity. And I've set this up for you so that I've had the B sub G given in reservoir barrels per MCF, in the standard nomenclature, reservoir cubic feet per standard cubic feet. Using a 0.6 gravity and 200 degrees Fahrenheit, I calculate a B sub G of this and get an 8% error. What should we do?
Solver.
Huh?
You can use solver to minimize
Yeah, minimize that error.
What variable am I going to change?
specific.
Yeah.
Okay, I've already tried that. So what it's going to do is it's going to make the specific gravity smaller. See, it reduces the error. Do you realize there's no hydrocarbon gas that is 0.5? Okay, so I've already thought about that. Okay, now you're taking the final exam, and you're at the point where everybody in class is right now. What are you going to do now?
Were we given the reservoir temperature?
No, you got it. You're going to pass this course. So let's see. I like to look ahead before we. I haven't tried this yet. Should we make the temperature higher or smaller?
Smaller.
Smaller?
I would guess so too, because although he uses 200.
But I only say that because back earlier in the course we had an example where you had assumed a temperature, but it wasn't actually given in the problem.
Yeah, I've done everything. Okay, it looks like we could hit it, doesn't it? Ooh, I don't even need solver. So let's try solver anyway. Data. We can use solver or data analysis. We'll use solver. Set this cell to be a minimum by changing the reservoir temperature. And see, that was ridiculous. A lot of times you're doing this better with 240. And let's try goal seed and see if that doesn't give us a better answer. Where's goal seed? What if?
Now, so you're saying that you've assumed a gas gravity and you're finding the the temperature?
Yeah, you're the one that jumped to this conclusion.
Whoa, whoa, whoa. I didn't jump to any conclusions. I would have tried to match both the viscosity and the B sub G
I told you all semester long that my BB uses a different viscosity.
Well, sure, but we might still get a better combination of values between gas gravity and temperature by matching, you know, two inputs, two outputs.
Viscosity is not going to go into my permeability equation in any shape or form or manner. So,
See, I was always like you said, I get sort of stuck when I'm trying to change two things is, you know, how much
Yeah.
you change one or change
Well,
the other.
that's what I said earlier in the course. We had an example just like this where we had to guess both of them.
Yeah.
And what I did is I made it match the viscosity and the B sub G. You know, you're guessing two values, you match two values, minimize the combined error. It worked really well.
you can do this with impurities too. That's probably, I'll probably hide it in the H2S on the final exam. I don't know. Okay. I would like to match the volumetric behavior. I know the textbook and I are using the same Benedict Webb Benedict Webb, no, I lost my last name, the third name of the author. For the B sub G, for the volumetric, because the only variable there is Z. We know the temperature, or we don't know the temperature, and the pressure. So temperature, pressure, and gas gravity. I mean, and if I go higher than point, he uses point, the author uses 0.6 quite a bit, then, so I'm thinking that I'm trying to outguess the author. I'm thinking to use 0.6 and use some other temperature or some combination of impurities, but I would have thought that they would have told me if they used those impurities. Anyway, let's move on. Let's use 240.
Well, I want to make sure that I understand you in a circumstance like this, where we've got multiple unknown variables such as composition, impurities, temperature, gas gravity, whatever. But you only want us to match one given variable, the B sub G. What's within play and what's not in play for guessing?
Well, everything's in play. You're just trying to make the best decision you can.
Mm-hmm.
I'm telling you, this is the best decision I can make.
Okay.
I'm going to change the temperature and match the volumetric behavior and ignore the viscosity. Now, I also have a problem in that I still have a 10% error in the total system compressibility, and that's with 100% gas saturation. And if I change that to 80% gas saturation, the error gets worse. I think he does run a lot of his simulations with 100% gas saturation, even though that isn't very real world. Okay, I'm happy. Everybody else happy?
I'm going to assume a gas gravity of 0.6. That's what I'm getting out of this, is assume a gas gravity of 0.6 and play with something else.
Just
We'll see how you do.
use a saturation of 110. It's probably-
Okay, let's move right along. Now, what did I say how we're going to solve this problem? I told you earlier. We're going to go to
Use
our...
the sister plots?
There you go. You're going to pass this course.
Okay.
Where do we get those?
Twice.
Don't we have a... I have to come all the way back here to get them. Somewhere in... Here we go. So we've been using the Bennett conductivity, constant pressure, constant rate. That's for buildups. Now we're going to use the constant pressure. It looks the same. It's different. See, it's 1 over Q sub D. It's 1 over rate. Okay? So I need a multiplier. I'm going to end up with a Q sub D. This is the situation I've been trying to build you up for. I've got no specialized plots. They haven't had project evaluation. I've got no specialized plots to analyze finite conductivity. And the other problem here is I got no cumulative production.
Right, right.
It's simulated rate data. I'd have to integrate the curve to get cumulative production, then I could plot reciprocal rate cum.
And we don't even do
And if I don't run out of time, we may start that. So I'm going to need a multiplier, but basically, let's say my multiplier is 1. I always start with 1, because I just need to get the calculation out of it. Equals, whatever my multiplier is, but then I don't multiply by rate, I need to divide by rate, right? I've got to divide by rate. I want reciprocal rate goes uphill, rate goes downhill. So D1's a constant, and my column C, see, I need these numbers to get bigger as they move to the right. And I should have put in here T sub D first.
Wait, so are we creating a
When we
column
have-
of
we don't-
reciprocal rates and then multiplying by a constant?
Yes.
Okay.
So what's my constant going to be here? I'm going to use 1 again. I always start my equations with 1. Equals this, absolutely, times my time. So now I got time, now I got T sub D versus Q sub D. I'm done. I just got to put my data on my graph and manipulate these 2 points. You see, I haven't had to do any work. Except for eventually I'm going to have to use these equations.
So did you multiply or divide by that math?
I'm always multiplied by my time on.
Okay.
There's reasons for that. T sub D is always equal to T times DI. This is actually defined, DI. Oops. Okay, so I just want to put this, I want to add this data to my graph, select data. And, you know, I usually like to put the problem number in here. Example 6.9. Here it is, right here. Select data. Add. Example 6.9. My X data is my T sub D. And my Y data is my reciprocal Q sub D. You see the relationship between P sub D and 1 over Q sub D? In P sub D, rate is constant. There's only one rate. Our last problem, what was it, 816 MCF a day or something like that. There's only one rate. Delta pseudopressure is, if it's a drawdown, is pseudopressure initial minus pseudopressure of the well flowing. So internally here we have something changing. In Q sub D, your delta pseudopressure, there's nothing that changes. You've got a constant pseudopressure initial and a constant pseudopressure flowing. What changes is your rate. So in reciprocal Q sub D, it looks exactly the same, right? Except for here, this changes. And I'm going to do this in black. For a drawdown, it's pseudopressure initial minus pseudopressure of the well flowing. And this changes, right? You draw a well down, the pressure draws down. So when we try to get P sub D, we set this up like this. And then typically when we get a type curve match, we solve for perm. Same thing we're going to do right now, except for delta pseudopressure is going to, we only have one PI and we only have one PWF. So that the only thing that changes is Q. So we're really going to, instead of getting a P sub D over delta pseudopressure match, we're going to get a Q over Q sub D match. Let's see which one we have. We actually have a Q sub D over Q, because we divided by Q. So we're going to get one, that equals 142. Anyway, we're going to get KH. We're going to get K before we leave. We'll get it in 10, 15 minutes. Tops.
I might have missed it. Why didn't you calculate TA?
I don't have any pressures, but that's a very good question.
Well, wouldn't it still correct for... Oh, it's a constant, isn't it?
Yeah, it's the same idea as that why we never correct T sub P, because we assume that we were producing at constant pressure. We don't have that history.
Right.
So if I'm producing a well at constant pressure, and the way I adjust my time is the fluctuation in the flowing pressure, it never changes. It's constant bottom hole flowing pressure. If I'm running a drawdown, my PWF is changing. I use that array of PWFs against the times that they've been acting at that PWF and calculate the viscosity and compressibility at that varying PWF.
But all those are constant because the conditions are
Yeah, I could actually do it, but it would have no effect. Very good question, though. I say after tonight, you move to the head of the class. Okay, I think I got everything. Okay, why doesn't it appear on my graph?
wrong multipliers.
The time varies are greater than.
Yeah, my Q sub Ds are too small, aren't they? See, my largest Q sub D is 008. It can't make it to my graph. How about we make it 100?
What's dead?
And then my T sub Ds are way too big. I gotta make them smaller. There's my data. Okay, I'm pretty close. Okay. You know, I'm probably good enough to the answer right now, but let's try to bring it down a little bit. Let's see if it fits the bottom one. Okay, what's the conductivity of our fracture? Yeah, or infinite. Now, I don't have a Green-Garten type curve for constant pressure production. This is all I got. Now, I actually don't have to do reciprocal rate versus Q for, I'm only talking to one person. I don't have to use reciprocal rate versus Q for this synthetic example because it's infinite conductivity. I should be able to plot reciprocal rate versus the square root of time. You'll get this in the next chapter. My theory, and I've never done this before, my theory is I can plot reciprocal rate versus the square root of time. And I'm going to generate a specialized plot. You know, when I go to all that trouble to make those symbols, I not only want to reset it, I want to get rid of the logarithmic scale. I not only want to reset it, I want to get rid of the logarithmic scale. And why do I have such a, why did it flatten it out so much? Oh, because the maximum is 1. There we go. So I'm expecting to get a straight line reciprocal rate versus the square root of time.
Because we're infinite acting.
No, it's because, well, yeah, it is because we're infinite acting, but it's because we're infinite conductivity.
Infinite conductivity.
Yeah.
Okay. And you
When-
do that by it crossing at the 0, correct?
I know I don't have a reciprocal rate Q to do that.
Okay.
We're playing, class. I've got reciprocal rate. I just want to. Why doesn't that cross at the 0? Oh, I know why. Automatic. Here we go. But you're actually right here too. This should cross it at that. Let's just see if this is a straight line. It's not bad now. So this is not truly infinite. What it is 500.
Right.
But as you can see by the way these lines are situated, the closer you get above 500, there's hardly worth having an extra line, except for there is an actual beginning to the linear flow, and there's actually an X on this where there's an end of the linear flow. So this is tailing into radial. Let's just do that. Well, we're working with pressure data. We could make up some
Is there-
other things.
There's an X on there somewhere?
Isn't there? Let's,
I can't tell. My dad has covered it up.
well, just delete it like that. Yeah, see, there's an X right here.
Oops.
And you can Control Z and put your data back in. See, it only took 5 minutes, except we haven't got perm yet. Now, I'll probably get it wrong the first time, but I have a Q over Q sub D. Do you see that?
Excuse me,
Yes.
can you please go back second shot? What you plotted?
What?
Kind of lost.
What?
I mean, what you plotted in the second shot.
Right, in the second shot,
Yep.
I made this up. Reciprocal rate versus the square root of time. For an infinite conductivity vertical fracture, that should be a straight line. It's pretty close to a straight line. This is not textbook or anything else. This is based on well, the author is Kern Guppy, but for infinite conductivity vertical fracture and linear flow, reciprocal rate versus the square root of time, and also versus cumulative production, should be a straight line going through the origin. Now, for finite conductivity fractures, there'll still be a straight line versus cum, just won't go through the origin, but it'll be a subtle curve. And you see,
So could it almost maybe look like it does?
it looks like, especially as noisy as production data actually is, it'll look like it. People will, a lot of people will still use square root of time. Okay, this was just, don't worry about this. You will not see this on the final exam. Okay? Do not worry about that. Okay, so we've got a pretty good match. Let's get perm. What do we have here? We're multiplying, all I need is this 80, okay? The only thing I don't know yet is this Q over Q sub D or is this Q sub D over Q? Because it's confusing. It's 80 divided by Q equals Q sub D. So what we have here is, oh, that's 1 over Q sub D. So if I multiply by Q, I have Q over Q sub D equals 80. Okay? Q over Q sub D equals 80. Anything will work. Here's an easy. Q, this is horrible. Okay, that 80 I have up there is Q over Q sub D. So 80 equals KH over 1422T. Now let's start getting rid of this other stuff. Okay? K, permeability, equals 80. That's what I got from my vertical match. You notice I've already got my pseudo pressures calculated up there. See where it says PI2400 and then highlighted in yellow? I got that. That can't be right. How come that number's, oh, this one's got a decimal in it. I knew that one had to be bigger than the other one. And then I need to get, I'm going to make, yeah, okay, that's the difference between those. So I've already built in for you delta pseudo pressure. Right there is delta pseudo pressure. It's confusing. That's delta pseudo pressure. Has nothing to do with this data right here. Okay, K equals 80. I wonder if I'll match the text this time. Times delta pseudo pressure. I calculated it for you. It's right there.
You lost your 80.
Huh. Where am I?
Start over.
You lost your 80. Temperature.
In the textbook, maybe when they show the solution, they use temperature. Maybe we can pick it out of there. Divided by H?
Times 1422, right?
Oh, yeah.
Big number.
That's way too big. Delta pseudo pressures upstairs. MCF a day.
I thought it was Q, the opposite. I think you said Q or QD. I thought it was the other way around.
I thought I got my derivation right.
Oh, no, never mind.
Oh, the 142, see the 142, yeah, 1422 T.
What are you using for PD?
I'm not using PD,
No,
I'm
it's
using
different.
1 over QD.
Oh,
You just erased it.
I erased it and rearranged it. That's not our permeability.
Wow.
So you don't need to.
Go buy the property.
Yeah.
Okay, I'll try this on.
It's just
Sometimes when I'm standing at the board, it's a little bit harder. And actually, it's in our textbook right here. We should be using this equation. How do I zoom? I hate this. It was right there. This equation right here on page 134. Except for, again, this is in a, We're using this equation right here, except for a P sub D over delta P match. We've got a Q over Q sub D match. Okay, but the form should look the same, 1422. But you see, I'm pretty sure my delta pseudopressure needs to be downstairs.
Do you have a PD there?
We got a 1 over Q sub D, not a P sub D.
Yeah, that's.
Let me start with this equation right here.
Put it down, you.
So P, instead of P sub D, we have a 1 over Q sub D. So Q sub D is downstairs. You see our delta pseudopressure term is downstairs instead of upstairs. And the 144, we have a Q over Q sub D, T, and an H. From what I can tell, the only thing is we got to change our pseudopressure from a times to a divide. What's the book give us for perm?
101.
there you go.
Okay, that's the only mistake we made.
So we need to
we
rewrite
don't
that
really have an
equation.
equation to use in this textbook, but, well, the reason we don't is because the way the textbook ran the example is they used a pair of pressure. But now that we know what we're doing, we could have, that would have been more helpful for than my derivation. And then when we get to this problem, what page are we on? 65.
So in both those equations that you had on the board, the delta pseudopressure needs to go to the numerator?
I can't answer that question because I erased too many things.
Well,
No, the ones that, what he had literally written on the board, because I wrote it down.
yeah.
I'm also going to look at this problem and see if they got temperature in here. When they, 6.7, we've already done that. We're doing 6.8, aren't we?
6'9", right?
6.9? See, this is the, we not started 6.9 yet? We're 6.10.
Yeah, we just passed it.
That was it. I only do the 2.
This is all broken.
Is this it right here for 6.9? 6.126?
20, 45, up to 11. those are that, and the one above it are the only two calculations.
Okay. And they don't, since they're using apparent pressures, and they gave us those things, they never had to tell us the temperature. Okay, so 0.01 must have been their match point. B sub G, mu sub G. Okay, and say they have a 1 over QD match point. Okay, but they get, is this their answer? Oh, that's,
Well, at the beginning it says analysis of the pre-fracture buildup test, GSK is 0.01.
why would they,
Further up. Keep going. Right there.
They give you a suggestion, right?
Yes.
we don't even need that, do we? We can calculate her. So now what we're left to is calculate X sub F, right? We can calculate perm.
If you put the delta P on the bottom, you get 0.014.
That's what we did, right? 0.014. We're good. We're better than the textbook. They had to tell us what the perm is, and we can calculate it. Using this type curve. Anytime you're on a type curve, if you can level set, you got perm. Going this way, on radial flow, you're getting e to the minus 2s. You're getting c sub d e to the t 2s. You're getting some combination of perm and skin. But for linear flow, you're getting X sub F. There's no wellbore storage and there's no skin. You're just getting X sub F. So the next thing to do is get X sub F, and I think we can get that directly from our, on page 134. We actually have the equation for this. It's in the table. Have I passed it? No? Pseudopressure versus delta T. So we can get, we have perm, we got 5 mu c sub T, and we got to make sure we're right side up or upside down on our delta T over T sub D X sub F. Function spacebar. We didn't really have a good equation for using the type curve here, but we do have one for calculating fracture half-length. X sub F. I'm not even going to try to figure out whether I should be right side or up. I'll just try it one way, and if I get it wrong, I'll be right the other way. Let's open a paren because let's open two parens. 2637, that's telling me I got units to hours, times perm. And my answer should be 50% higher than theirs because I'm using 0.0147 and they're using 0.01. Divided by 5 mu c sub T. That closes the paren for the denominator. I don't think I need an open paren there. And then I just multiply, and I may have to change this to divide. I'm just going to do the easiest thing I can do. Here's my multiplier,
Just
and
divide.
then close my paren and raise the whole thing to the 0.5. If I get a ridiculous number like I did, then I should be dividing rather than multiplying. 730. Textbook got? Oh, we're way down here, aren't we? What page is this on? 146?
No, 48. All right. Yeah, 650.
651. Right?
What page? Is that
Page
exhibit?
148.
It's 7:30.
Oh, I see. $651. And we're getting 730. Again, I said we're going to get higher because we're using a higher perm. If we kick in 0.01, we're going to get a lower number. Okay, so the textbook didn't realize we could get perm all on our own. Now, this is not transient pressure analysis. This is transient rate analysis. This is chapter 9 stuff. And you might remember the very first example we did was a variable rate drawdown. A variable rate drawdown is transient rate analysis, not transient pressure analysis. So now we've actually done a radial flow and a linear flow transient rate analysis already, even though we're in chapter 6. It's the same. It's just changing the inner boundary condition from constant rate to constant pressure. Okay. That's pretty good timing. Okay, so what's going to happen next? We'll finish off this chapter next week. The next week, I'll start a new material, but answer any questions you have. And then the next week will be a test over linear flow. So I'll add some material next week. Don't we have 3 weeks? Am I miscalculating?
2 weeks.
2 weeks. Two more weeks.
The test is 2 weeks from today.
Text is 2 weeks from today.
So one more
I don't think I have too much.
So next week's our only week to ask questions on.
That's what I'm trying to get to.
Yeah. Okay.
I think you said it, right?
Yeah. No, I didn't. I was thinking there was 2 more weeks in there. I was going to start another. So I think there might be a little bit more, another example that I can work next week.
610.
610.
There's 610?
Yeah, there's a 610. I'll work 610 next week and answer any questions. I encourage you to try to work the exercises on linear flow at the end of the chapter and see if you have any questions. Because it'll be the same questions that you'll have during the next test, but I won't be able to answer them. Okay, see you next week.